Brian Greene, welcome to the show.
Thank you so much.
The Elegant Universe turns 25 this year, just like me.
I wish I could say that about myself.
I'd like to get into what's changed, where we're at, but I think it's going to require starting with the question that I'm sure you've never been asked before. What is string theory?
Yes, good question. There are a number of ways of framing what string theory is about, but perhaps from the largest perspective, it's an attempt to realize a dream that really begins with Albert Einstein, which is this idea that we have a single universe, so we should have a single theoretical explanation for how that universe works. And that single explanation should be mathematical. And so there should be some grand mathematical formula, some mathematical equation that would describe everything in the universe. And Einstein sought this so-called unified theory for decades, but he never found it. And string theory just may be the theory that Einstein was looking for.
Now, what kinds of problems is the scientific community faced with that leads them to come up with something like string theory? I mean, we already had a lot of ideas about what the universe was made of, the different constituent particles and stuff. So where do we get this vibrating strings thing?
Yeah, absolutely. So from my initial description, it might seem like it was more of an aesthetic or a philosophical motivation to try to find this unified theory, but it goes far deeper than that, because there are these two main ideas, two main pillars that support physics as we have understood it since really the middle of the 20th century. And that is quantum physics, which describes the smallest things in the world, the elementary particles that make up matter, and Einstein's general theory of relativity, which really describes the biggest things, where gravity matters, stars, galaxies, black holes, the entire universe. And the problem is that even though quantum mechanics works incredibly well in the micro domain and general relativity works incredibly well in the macro domain, whenever you try to put the two mathematical theories together, it breaks down. When you do any calculation that blends the math of quantum mechanics and the math of general relativity, you get one single answer, and that answer is infinity. And infinity might sound, well, that's kind of, cool and poetic sounding, but it's nonsensical in the context of physics. There's no quantity that you can measure that's ever infinity. So infinity is a diagnostic, which basically the mathematics uses to kind of grab us by the lapels and slap us in the face and say, you are doing something wrong. You've got to find a new description that puts quantum mechanics and general relativity together. And that is what string theory does, at least in principle on paper. And I need to stress that. This is not a tested theory. We don't know if it's correct, but mathematically for the first time, it does show a way of bridging the gap between these two theories.
So does this tell us that of general relativity and quantum mechanics, at least one of them is sort of wrong? I mean, people often talk about general relativity as coming along to replace Isaac Newton's understanding of gravity, and they say Newton was kind of almost there, but ultimately he was wrong. Is that the same approach we need to take of something like general relativity as well?
It is, but I would caution to see it in that historical context that you've just made reference to, because it's a little strong to say that Newton was wrong. I would say that any physical theory that we ever write down is meant to describe the universe in a certain domain. And when we gain better equipment and when we make progress, we try to extend the domain of applicability of our understanding. And when we do that, we almost always find that the ideas from the earlier generation, yes, they really work in the original domain, but when you go beyond that domain, you need to update them. You need to replace them. And so Newton did a wonderful job at describing the orbits of the planets. General relativity comes along and says, well, actually, if you go a little bit further than just the orbits of planets, if you want to understand more extreme environments like black holes, then you need these new ideas of the general theory of relativity. And that is indeed the process that we feel we're likely recapitulating now. Because when you try to put quantum mechanics and general relativity together, you do find, at least in the string theoretic context, that general relativity has to yield to additional terms, additional mathematical constructs that Einstein himself did not write down. And so, yes, as we try to go beyond even the domain that Einstein successfully described, when we try to put quantum theory into the story, which Einstein did not do, we do find that general relativity gets modified. Now, it could also be that quantum mechanics gets modified. This is an idea that people are talking about today. So that would, again, fit into exactly the same template. Earlier ideas, when you try to go further, require new concepts, new ideas. They have to be modified.
Do you think that there is a sentimentality in physics where people kind of want to cling on to these famous revolutionary ideas because, as well as them being really impressive as theories, they're exciting, you're familiar with them. And so when you're faced with something that causes you to abandon something so familiar, do you think there is a psychological barrier for a lot of physicists?
I think it's really depending on which physicist you're talking about. So are there some in the history of physics where you can find reasonable evidence that they were reluctant to take the new step because they were so tied to the old way of looking at things? Yes, you can even in some way say that about Einstein in some ways. When quantum mechanics came along and was suggesting that the best you could ever do is predict the likelihood, the probability of one or another outcome, very different from the classical perspective that Einstein was used to, where you tell Einstein how things are today, and Einstein will tell you how they will be tomorrow with 100% certainty coming from the mathematical equations. When quantum mechanics began to chip away at that picture, yes, is there some evidence that Einstein resisted it? Absolutely. But I would say that the dominant perspective of most physicists, including Einstein himself, is that it is so exciting when there is a radically new way of thinking about the world. And so I would say the dominant way in which physicists approach their work is that they look for the opportunity to take us to a new place. And so while, yeah, I mean, you know, we do get comfortable with certain ways of thinking about things, in the end of the day, most of us are all too happy to be part of a revolution if that revolution is well motivated by experiment and theoretical calculations.
So, string theory. What are the strings of string theory?
Yeah, so when we get into the details of this approach to put quantum mechanics and general relativity together, we find that historically, the essential move was to say, look, the old paradigm is that matter is made up of these little particles, electrons and quarks, little tiny dot-like structures. The new idea of string theory was to say, what if they're not little dots? What if they are extended little filaments? What if you took a powerful microscope and you looked into the heart of matter and you didn't find a swarm of little dots, but you found a swarm of little vibrating filaments? And the motivation for that came from the fact that with that move, the tension between quantum mechanics and general relativity went away. That little tiny move from dot to filament was what you needed for the mathematics of these two theories to harmoniously meld together. So if this picture is correct, the electron would be a little vibrating filament, and the quarks, they would be little vibrating filaments, and the different vibrational patterns, like the different musical notes on a musical string, would correspond to the different particles that make up the world. So it's kind of like the universe becomes this microscopic cosmic symphony of vibrating filaments. It's a very beautiful and poetic picture that we can make rigorous and mathematical.
And mathematically beautiful as well. So I keep getting told I'm not a mathematician, I couldn't possibly vouch for it. But it does sound a little bit like, I mean, you told me a second ago that string theory hasn't been proven. It's not been sort of experimentally verified. I was under the impression that the thing that was so great about the scientific enterprise, physics, is that we can do that. We can have hypotheses, we can test them, we make predictions, and if those predictions come true, that's how we know we've got a good theory. This sounds a little bit like it's working in the opposite direction. We've got this problem, and here's a mathematical way of thinking about it that will plug in those gaps. But is that an appropriate way to be doing science?
Well, I would say it's not really going against the grain of what we always do. It's more that the timescales involved for being able to check the mathematical predictions are much longer. Even in this case, we don't know how long they will be compared to things in the past. So take Einstein and his special theory of relativity. There was a real puzzle that he faced, which had to do with properties of light and its motion. He wrote down some mathematical ideas just out of his head and thinking about the data and the situation. And very quickly, those ideas could be tested. In the general theory of relativity, 10 years later, he writes down equations to try to gain some insight into problems to do with the force of gravity. Within 4 years, you could test those predictions through the solar eclipse of May 1919. So there's a 4-year gap between the math and, say, the confirmation. Here we are with string theory, and I don't know exactly where you want to date the theory from, but give it sort of, 30 years or ish, something, 40 years, and we haven't been able to test it. So the time scale is longer. Will we test it in 50 or 100? I don't know. It really depends on how quickly our mathematics continues to develop and, importantly, how quickly our technology continues to develop. That's really part of the problem here. Any theory, I don't care if it's string theory or loop quantum gravity, another approach that people have developed, if it's putting gravity and quantum mechanics together, it will distinguish itself in realms that are incredibly tiny or incredibly massive. That's where the tension between general relativity and quantum mechanics surfaces. And so you're going to have experiments that can probe incredibly small or incredibly energetic realms. And we are reaching, I wouldn't say the limit, but a challenge to go beyond, say, the Large Hadron Collider in Geneva, Switzerland. We used to have small colliders, bigger. Now we've got this 18-mile circumference accelerator. How much bigger can you get? And we don't know that we can get to the scales necessary to test these ideas, because if you naively look at how big the accelerator would need to be, it would need to be as big as the galaxy. That's how much we've leapfrogged mathematically. And that's what distinguishes this situation from, say, special relativity or general relativity or the standard model of particle physics.
Well, how is it possible in principle, even if we did have some galactic, collider, how do we experimentally confirm that all fundamental matter breaks down into vibrating strings? How does that
It's the key question. And if you allow me to imagine that we had arbitrarily energetic equipment, arbitrarily able to probe to increasingly small scales, or maybe we talk to an alien civilization and they've cracked this problem. Are there tests of string theory? Yeah. String theory says that if you were to slam particles together at sufficiently high energies, we would see things that string theory predicts that you would not see in more conventional approaches. And we could write down what those features would be. So in principle, they would be testable.
Those are like new kinds of particles?
New kinds of particles, the way in which the particles slam and bounce off of each other, the so-called scattering amplitudes, they're different in this approach than they would be in a more conventional approach. And so there are diagnostic tests that in principle we could carry out if we had this arbitrarily powerful equipment, which we do not have.
We'll get back to Brian Greene in just a moment, but first, do you trust the news? I don't. And a lot of that has got to do with the bias that inevitably seeps into reporting. Wouldn't it be great if there were a way for us as consumers of news in this media landscape to navigate bias, objectively comparing the way that different sources are reporting on the same story? Well, luckily, that is exactly what today's sponsor, Ground News, allows you to do. Ground News aggregates thousands of local and international news outlets all in one place so you can compare reporting across the political spectrum. Try it out at ground.news/AlexOC. Take a look at this story about how 1/5 of pollinators in North America are at risk of extinction. On Ground News, I can see that of all the sources reporting on this story, only 9% of them are right-leaning. This means that if you only normally tend to read right-leaning news, you could have missed this story altogether. And Ground News even has a dedicated blind spot tab, which specifically seeks out stories that you would otherwise miss based on your specific reading habits. Nowhere is doing news aggregation like Ground News. Try it out for yourself at ground.news/AlexOC or by scanning the QR code that's currently on your screen. Use my link to get 40% off their unlimited access Vantage plan. That said, back to Brian Greene. What do you think Einstein would have made of string theory?
Well, I think at first he would have resisted it a bit because it does involve some pretty far out ideas. And so, as you were saying, it does take a while for even psychologically people to acclimatize to a different way of thinking about things. But I have little doubt that if Einstein took the time, and I think that he would, to sit down and learn about these ideas, the fact that it involves his own general theory of relativity, the fact that it does incorporate quantum physics, which he resisted but ultimately recognized was a powerful way of describing the world, the fact that it involves extra dimensions of space, an idea that Einstein himself spent some time thinking about. All of these ingredients, I think ultimately Einstein would find exciting. And mathematically, I think he would be bowled over by the beautiful way in which string theory brings it all together. I do think he would ask the very same question that you did. How do you test this? How do we know that this isn't just pure mathematics? And that would take us into a wonderful conversation along the lines of the material that we just discussed. So yeah, I think he would warm to these ideas pretty quickly.
Do you think we're sort of in the realm of philosophy here? One of the criticisms that I see of string theory as somebody who doesn't understand the first thing about it is that because of this lack of experimental data, you can say that in principle it could be tested, but there are all kinds of philosophical theories that in principle we could test. Ideas about personal identity or Star Trek teleporters, and would the person still be the same person if you reconstructed all of their atoms? I can sort of hypothesize a way to test that in principle, but because that is so far-fetched, it's squarely in the realm of philosophy rather than science. Do you think that string theory, for that reason, might belong there, at least for now, too?
Well, I guess two quick things. One, there are some who would view a categorization of being in the philosophical domain as somehow denigrating the ideas. And I don't see it that way at all. I mean, if we are in a philosophical realm, fantastic. Philosophy is wonderful.
Yeah,
you know,
up, if you ask me.
Yeah, exactly. So, so I don't view that as some kind of a black mark against a physical theory if it raises philosophical questions. But you're saying something slightly different. You're saying because we can't directly test it, should it be called science? Perhaps we can frame it that way.
Yeah.
And I think the answer to that is absolutely yes, because science is not about ideas that can be put forward and then tested immediately. Science is about putting forward ideas that solve critical problems that can be tested, at least in principle, at some point. And that's really important, because if you put forward an idea that's meant to be scientific, but someone can establish you can't possibly in any way, shape, or form ever test that idea, then it's hard to see that it fits within the categorization of science.
Sure.
But if you put forward an idea, which at least in principle you could test if you had the right equipment, then to me, if it solves certain key problems, if it advances your understanding theoretically of things like black holes and the Big Bang and the nature of space and the nature of time, which is what string theory does, then it's absolutely worth you're investigating it, and it absolutely falls squarely in the realm of science.
But it also raises certain problems as well as solving problems, right?
Yeah.
I mean, there are problems in the sense of just counterintuitive implications. Like, I don't know how many dimensions is it that we're supposed to believe in these days? 11, 12, 30? I think it
11's a good number, yes.
Depends who you ask, which typically is quite difficult for people to imagine and to swallow. Although, as far as I understand it, there's something about the way that strings vibrating in these dimensions, there's something about that which would produce the long sought after graviton particle, right? And so scientists for a long time have expected that there would be this particle called the graviton, which is like the fundamental unit of gravity. And if you do the maths for string theory, you predict this graviton. And so when people say that string theory has no predictive power, it's like, okay, we haven't made a prediction of something that we don't know if it exists yet and then found it. It does predict one important thing, which is the existence of gravity. Of course, we've known that gravity has existed for a long time, but we haven't actually been able to find it in the way that maybe string theory can, right?
Yeah. So, I mean, I'm fond of taking that line of discussion too, but I think of it more as a post-diction rather than a prediction for the very reason that you mentioned. We've known about gravity. Isaac Newton wrote down a mathematical understanding of gravity. But if you imagine a counterfactual universe, for instance, a universe in which there was no Einstein, and we did not have Einstein's general theory of relativity, and yet somehow people came upon string theory, and they began to study the mathematics of string theory. Within the math of string theory, a clever string theorist would extract the general theory of relativity.
Wow.
And so that feels very gratifying, that these ideas hold together with such a rich and powerful cohesiveness. And you're absolutely right, because quantum mechanics is also part of string theory. It wouldn't just be the general theory of relativity. It'd be the quantum version of the general theory of relativity, which does involve these particles called gravitons. So string theory naturally does give rise to the quantum mechanical carrier of the gravitational force, which is the graviton. But look, I need to emphasize, no one's ever detected a graviton. It's the smallest particle of the weakest of all forces. So we're not surprised that it's been a challenge to ever capture a graviton and detect it directly. We're not surprised by that, but it is a beautiful thing that this idea that predates string theory naturally yields the very same structure when you study the math of string theory.
Yeah,
that's nice.
It's in the maths. That's the interesting thing. Now, one thing that I'm a little bit confused about is how something about these different dimensions and the different ways that they could exist, the different sort of structures that they could have. I'm not sure if it's related to the dimensions themselves or the shapes or whatever, but I hear a lot of people talk about how string theory points towards this explosion of multiple universes, some kind of multiverse picture. I don't know if it produces like a potentially infinite number of universes, or if it's like some precise number of 700,046 when you actually do the calculation, but something about lots of universes.
Yeah. So when I was a graduate student way back in the 1980s, long before you were born, and I began to work on string theory, the aspect that caught my attention was its need for these extra dimensions of space. And briefly, when you study the math of string theory, there's an equation, and the equation cannot be solved if there aren't these extra dimensions of space. So that's where the idea does come from. And when I was a graduate student, people began to think about what those extra dimensions of space might look like. The idea is that they're very small, they're crumpled, they're all around us, but they're so tiny that we can't directly see them the way we can directly see, left, right, back, forth, and up, down, right? The three dimensions of common experience. And so if they're crumpled up, what's the shape into which they are crumpled? And in the mid-1980s, scientists, mathematicians wrote down 5 possible shapes. And at that point, people thought those might be the only possible shapes that would meet the mathematical requirements. So as a graduate student, I started to study those shapes to see what physics they might give rise to. And that's what my doctoral dissertation was all about. And that seemed kind of a beautiful thing. A small number of possibilities. Maybe we can either rule them all out and get rid of string theory, or maybe one of them describes our world, and wow, that would be amazing. The problem is, as you made reference to, as people began to study the math further and further, 5 possible shapes grew to 6, grew to 10, grew to 1 million, grew to 1 billion, grew to 1 trillion, grew to 10 to the 500. That little list of 5 possible shapes is now an enormous list of possibilities. And so what do you do with that? Well, one idea that people put forward is maybe all of them are real, in the sense that all of them are realized, in the sense that there are many universes in which each of those shapes constitutes the extra dimensions in that universe.
Yeah.
And this is an idea that really was spearheaded by Leonard Susskind, who was thinking about these ideas in the context of inflationary cosmology and in the context of a puzzle called the cosmological constant problem. And when he put all these ideas together, it naturally suggested that maybe there are multiple Big Bangs yielding multiple universes, each with a different shape for the extra dimensions. That's where this multiverse comes from.
And that's because of the possibility of different ways that these dimensions could be shaped and organized. To me, I mean, that is of course really interesting, but a lot of people will listen to that and think, what if there's just some other reason why the dimensions are as they are in our actual universe? I mean, the fact that a bunch of other realities are mathematically possible doesn't mean that they actually exist.
Yes.
Is positing that they just do exist just sort of a convenient way to get around the problem of explaining why the universe is the way it is?
Yes, that is certainly a possible way that this story might ultimately be told. And it could be that there is some mathematical equation that we've yet to find. And when you look at that mathematical equation, you solve it, and maybe it says, that's the shape 22,462. Maybe that will come out of some fundamental mathematical calculation, at which point we'll say all the other shapes were spurious. They were potential shapes when we didn't know about this other mathematical condition, but with this new condition, they're gone. And there's just this one shape. And that would be a very beautiful resolution to all of this. We've yet to find anything like that equation.
Would we have to rule out those possibilities? Because such an equation would say that all of these trillions of other potential ways of organizing the universe actually can't obtain. We just didn't realize it before. Would we have to show its impossibility in that sense to show that it didn't in fact exist? Or is there a world in which we can prove actually they are all definitely possible, and yet we know that they don't exist?
Sure. It could just be historical contingency.
Yeah.
If we understood the origin of the universe better, and if we understood the dynamical processes by which the universe evolved from however it began to its current state of being, maybe when we just look at that history, we go, oh, look, that shape is picked out by the historical progression. The others are possible. They solve the equations. They're just not realized because of the particular set of steps that took us from the beginning until today. That's another possibility. But I do want to emphasize that when Susskind was thinking about this, he was thinking dynamically, because when you look at this approach to cosmology called inflationary cosmology, you find within it very naturally that our Big Bang was not a one-time event. You find very naturally from the mathematics that our Big Bang would be one of many Big Bangs, giving rise to one of many universes. And Susskind simply said, if we port that idea from inflationary cosmology into string theory, then very naturally those distinct Big Bangs could have distinct shapes for the extra dimensions.
Man, so I'm thinking there's something quite profound underlying all of this and all of these considerations. And what's coming to mind for me is that you talked before a little bit about these particles, these potential gravitons, but also have quarks or however you want to say it. And you've got neutrinos and you've got electrons. And part of the story of science is trying to explain why that is the way that it is. I mean, so much of science is descriptive, right? Like we look inside of an atom and we find that it's made of protons, neutrons, and electrons. And we feel that thereby we've sort of explained something. Like we understand the atom. Whereas, as far as I'm concerned, all we've really done is just described it in further detail. And we haven't really shifted the needle on the question of why it is that way rather than another. So when we look and the quantum realm and we find these very specific set of particles and not other particles. They've got particular weights and not other weights. Why is that the case? Why not some other set of particles with a different set of properties?
Yeah. And so it really comes down to, what do you want science to do? Niels Bohr, the grand master of quantum physics, would say all you want science to do is give you some mathematical explanation for the readouts in your equipment. You take a measurement, you get a result. Can you explain that number? You don't need to explain anything about the nature of reality. You don't have to tell a narrative of how things are. Can you explain those numbers? Now, many of us think that that's a too limited way of looking at science. I'm more in the camp that you describe. I want to feel like I can tell some coherent story that gives me some understanding of not only how things are, but why they are this way. Now, we've been really good at the how so far because we have the standard model of particle physics that can describe the results that come out of every experiment at the Large Hadron Collider, gives us an understanding of the structure of matter, gives us an understanding of how that matter can ultimately coalesce when you put Einstein's ideas together into stars and galaxies and into planets. That's all pretty good. But if you then said to me, but in that theory, you've made certain assumptions.
Yes.
You assume there's electrons, neutrinos. Yep. Why those particles and not others? And that really comes down to the question that Einstein really asked in a way, is there a unique universe that somehow is logically required to be, and any deviation from that universe would somehow be logically inconsistent? Einstein said, did God have any choice in creating the universe? Could God, therefore, in other words, have created the universe differently, or was God's choices fixed by some sort of master logic that we've yet to uncover? I would love if we find that logic. We're nowhere near that. As of today, is it possible logically and mathematically that there would be a universe that has vastly different particles from the ones that we know about? I think so. Is it possible that we could be in a universe where it was all Newton, no quantum mechanics? Is that a logically possible? I think it is. Now, people will argue about this, but I don't think that we have any criteria at the moment where we can say, the universe had to have quantum mechanics. It had to have general relativity, has to have electrons and quarks. There's no other reality that could possibly have been realized. We're nowhere near that goal, but it would be wonderful to get there. And ultimately, frankly, we'd like to go one step further and answer Leibniz's question, why is there something rather than nothing? Nothing seems to be logically possible too. And by nothing, I don't mean, and neither did Leibniz, empty space. I mean nothing. No space, no space, no time, no nothing. That seems to be logically possible. And yet, clearly, we're not in that reality. Why not?
Yes, that to me is the foundational question, in the sense that it's really kind of naive and simple, like a kid can ask it, but it's also like the most profound philosophical question that you come back to regardless of how much study you do. I am suspicious about the extent to which science can inform a question like that. An analogy that I've given before is a bit like discovering a book. There are some books on the table, which are also available on Amazon.com and reputable booksellers everywhere. But suppose it were a book of poetry on the table. I use the example of a Shakespearean sonnet, a book of his sonnets. And we just discovered this book. And we wanted to know what it's doing there. What is it? What's it made of, right? And so we start studying it. We start looking inside. And some clever person begins to notice that it follows certain patterns. At the end of these things called sentences, there's always a period, a full stop, right? And there are these big versions of letters and little versions of letters, and you discover this law of capitalization. And then the really clever person realizes that when you pronounce these words, it follows this rhythm, dun, 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 dun. and they call it iambic pentameter because, it sounds fancy, but they've identified this law of iambic pentameter that everything follows. And somebody says, look, we're discovering all of these laws of this book. Isn't it amazing? And I'm still left with the question of, why is the book there? Why does it follow those laws? Why was it written in the first place? And for somebody to say to me, well, we don't know yet, but look at all the progress we're making. Look at how much we've discovered. Look at how many laws we've uncovered. Surely at some point we'll get there. That would be a category error, right? Because you're never going to push the laws of literacy enough to understand the origin of the text. And I wonder if there's an analogy here when we look at the laws of physics and we discover the way that planets orbit each other and stuff, and we're finding all these wonderful descriptions of how everything works. Is it a category error to suggest that if we just push that kind of thinking far enough, we'll get the answer to the origin of the universe?
It could be. I don't think it is, but I need to qualify it in two ways. Number one, I would say what physics is about and how it differs from your analogy with the sonnet is that physics is about finding a description that involves far less input and far less information than the things that comes out of it, the ultimate description of what's going on. So when we look at quantum phenomenon, there is so much stuff that happens in the microscopic world. Particles slamming into each other, joining together into atoms and into molecules. So we can describe the fundamental processes with a few lines of mathematics. So that complex amalgamation of processes is reduced to a few symbols on a piece of paper. It is ultimately just a description of what's going on, but it is a very efficient and effective description. And it's so good that when we use the math to calculate, for instance, magnetic properties of electrons, we can make a calculation to 14 decimal places, and then we do the experiment, and it agrees digit by digit by digit to 14 decimal places. You can't help but think that that's more than just a mere repackaging or a mere observation about the patterns. You're somehow finding something at the heart of the patterns when you can make that kind of a leap from mathematics to predictions. But I would say that I do differ from my colleagues in a way that's relevant to the analogy that you give, which is the following. The sonnet, I think we'd all agree, is a human construct.
Yep.
The description that you gave in terms of capital letters, small letters, periods, iambic, pentameter, those are all human inventions.
Yep.
You can use the word that you did use, discovering these patterns. You are discovering them, but the patterns were human inventions.
Yep.
And I think that what we're doing in mathematics is really just inventing human inventions, a language that's really good at encapsulating the patterns not found in a sonnet, but the patterns found in nature. And so I don't think that we are discovering laws, even though in loose language I often do say that. I think we are inventing laws. We're inventing the math, we're inventing the symbols, we're inventing the operations, and we are inventing the equations and finding, wow, these equations are really good at encapsulating those patterns. In fact, they're so good that we can use the equations to make predictions about patterns we haven't even yet seen. And then we do go out and we see them. So it is powerful, but ultimately, I think that what we're doing is inventing things. So now back to your key question. Could that invention ultimately give us answers to these profound philosophical questions? And I think that they can point the way because the equations are good at finding the patterns, encapsulating the patterns. And if you believe that reality, for reasons that we don't understand, does follow patterns. Did God infuse those patterns? Are they somehow written into some ultimate description of a universe that has to be that? I don't know. But if you believe that there are these patterns and we've invented a language that's really good at talking about those patterns, then yeah, in principle, maybe that language can point us toward the ultimate pattern, which may give insight into why there's a universe at all.
Patterns is a really interesting way of describing it because I wanted to know what your view is on what a law of physics is. These words like laws, these words like forces, the force of gravity, they're thrown around without people stopping to think about what they're actually saying there. I mean, to say that there is a law of physics, that word seems to imply that there is this written rule somewhere that everything is following. The question that got me thinking about this when I was younger was to ask, like, do things fall to the ground because of the law of gravity? Or do we have the law of gravity because things fall to the ground? And it seems more sensible to me to suggest that, like you indicate, we are essentially describing patterns that we see. And the great observation of David Hume was to realize that that is just something that we observe and describe. He looked everywhere he could for the causal connection between hitting a billiard ball and that billiard ball going forward. And he thought there's nothing in principle, logically, like preventing me hitting that billiard ball and it flying upwards instead of forwards, except for this thing that we observe called causation. But he looked for it everywhere and he just couldn't find it.
Yeah.
But he said, but I still believe in it, though. I still believe in causation. I just have absolutely no way to justify its existence. And the problem for Hume is that the way that Bertrand Russell put it was, in this problem of induction, was to say, like, if you were a chicken and every single day the farmer comes in and throws your seed, right? And so the chicken develops this connection between the farmer coming in and the food being given, in the same way that every time I've seen an object be dropped, it's fallen to the ground. So I developed this idea of a causal connection just because every time I've seen it, that's what's happened.
Yeah.
And Russell's like, well, the chicken will in the same way develop a causal connection between the farmer coming in and the food being given. But
until the hatchet comes.
Quite right.
Yes.
Until the hatchet comes and the chicken's dead.
Yeah.
And we realize that the chicken was just identifying patterns, but there was no actual law.
Yeah.
It feels ridiculous to suggest that the laws of physics could work in the same way because it's happened so many times.
Yeah.
Every single time we've ever seen this kind of stuff. But like, is there this thing called a law that makes sure it happens, or are we just describing patterns?
And look, so I would say, number one, when I was younger, if we had this conversation when I was your tender age, I would sit here and say, yeah, there are laws of physics. Yes, when we write down these mathematical laws, they are why the universe behaves the way it does. And that was so naive as I look back at my 25-year-old self thinking that way. Because, number one, obviously, laws that we write down change over time. So number one, we have to recognize it's all provisionals. But even more deeply, in the end of the day, what we humans do, we are able to access a tiny part of reality. We find patterns in the part that we have access to, and we invent this language that does a really good job at describing it. And that's really, I think, all that there is to it. But having said that, I'm not precisely sure the language, and I always struggle at this point to find the right words. I do think that within the fundamental architecture of reality, there are certain inbuilt patterns that do guide the dynamics, that do guide the billiard ball as it slams into another billiard ball. I don't think it's Newton's laws. I don't think it's the laws of quantum physics. I don't think it's general relativity. But I do, within the architecture of reality, feel that there is something that requires this kind of regularity. Now, is that a law? I'm not sure if that's the right language any longer, because the universe just does what it does. Particles move and billiard balls slam into, and they don't care about quantum mechanics or the laws of physics as we articulate them. They're just doing their business, and they've been doing that business long before we existed, and they will be doing their business long after we are gone. And so in that sense, the universe just is and just does and just evolves. But I do think there's a fundamental regularity that guides how things progress. Do we have access to that regularity? Is math the right language for articulating that regularity? I have absolutely no idea, and I don't have any reason to believe that it is. I do know that it does a really good job at approximating those regularities, which is why we can make predictions that so closely match observation. But does that mean that we've actually uncovered the true fundamental regularities of reality? That, to me, would be a miracle.
Would that be something material in your view? I mean, I tend to agree with you that there is something about the nature of reality that I don't think gravity is going to switch off in 5 seconds. But then, let's not tempt the gods. I do think that there's something holding this all together. But if we're talking about the thing that governs the interactions of all material objects, essentially, does that governing thing itself have to step outside of materiality, and we get into this realm which physicists often dare not tread of talking about immaterial influence on immaterial things?
Yeah, look, well, 3 quick things. Number one, we've looked at the universe by using powerful telescopes way back to few 100,000 years after the Big Bang. So say we've looked at it through a 13 billion year span. That may seem like a long period of time, but we can extrapolate into the far future, and there's every reason to believe that this cosmos of ours will exist in one form or another for 10 to the 100 years, if not longer, into the future, which means that we could be like the chicken. And for 13 billion years, we've seen the regularity, but maybe, 10 to the 100 years from now, the hatchet comes and we realize, we were just confused by the patterns that held true for such a long period of time. Yeah. So is it possible that gravity will switch off? Probably not in 5 seconds, but we're looking at a tiny region of time compared to the entirety that might happen. Number one. Number two, do we step outside of materiality? Look, I'm open to that idea. I would be thrilled if that were the ultimate answer. How remarkable if there is some grand non-physical entity that is responsible for the universe and the fact that we're here. I would love to learn about that, and it would be enormously exciting. The problem as a physicist is I can't go any further than that excitement. I can't analyze it. I can't investigate it. I can't write down mathematical equations. By definition, it stands outside the physical, the thing that a physicist focuses upon. So I don't find it that interesting. I don't say it is impossible. It just doesn't occupy my attention when I can't go any further in the analysis. And so my perspective has been to say, sure, maybe, but now put that to the side and see how far I can get just focusing on the physical, just focusing on the tools that we have developed. And the fact that we've been able to go as far as we've been able is deeply thrilling.
One of the most celebrated descriptions of the universe that has come about of late, and by of late I mean in the history of the scientific enterprise, is this surprising fact that so much of what governs our universe, the strength of various laws, for example, the mass of various particles, are so finely tuned that some theorists do suggest the multiverse we were talking about earlier, to the extent that the only way to explain the fact that it could have been so many ways and is this way is that this is just one of many universes. Another suggestion for that, from that, is to extrapolate and say, well, there must be some kind of necessary reason why these laws are the way they are. That's the kind of thing that the physicist is looking for. The third option is this sort of supernatural intelligence. Many people think that, I understand what you're saying, that the physicists can't go beyond the physical, but we can extrapolate explanations from the physical data, right? In the same way that if I were to look at some evidence around me, if we all left this room and somebody came in and saw that there were some glasses on the table and saw that there was a book placed kind of in the middle of the table and all this kind of stuff, they didn't see any human beings, they didn't see any agents, but they can just extrapolate from the arrangement of the descriptions that they see of the way the room is. There must have been somebody there. In the same way, the physicists might not be able to sort of look beyond the material, but can they look at the strength of the strong and weak nuclear forces, and the fact that if gravity was a tiny little bit stronger, the universe would have collapsed in on itself, and a bit weaker, and everything would have flown apart, and think, I can't see any evidence of design directly, but I can extrapolate from that there must be some kind of intelligence behind the universe.
Yeah, so bear in mind, number one, often people do say that if you change the value of the physical parameters just a little bit, the universe as we know it goes away. The problem with that is we can only do that analysis if you change the parameters by a little bit. If you allow the parameters to change by a lot of bit, not a little bit, and you allow many of the parameters to change simultaneously, nobody can really say what that cosmos would be like. And so it's possible that there are patches in parameter space where you would get different kinds of universes that perhaps would give rise to different living systems. And then each living system in its universe looks around and says, wow, this universe is so special. It must be that there's some kind of, grand design that got us here. But they're all saying that in their own parameter space because they're all making this mistake of only looking in a small neighborhood around the point in parameter space where they exist. So that's point number one. And so part of it is we just don't really know enough to make...
If we turned up gravity a little bit...
And left everything else the same, I agree.
But if we turned it up to 11, that somehow...
Right.
That might...
Yeah, but what if you simultaneously turn up the repulsive force that might come from a universe with charged... I mean, it's a highly complex problem.
And there might be something about turning up gravity which necessarily also correlatively turns up this repulsive
conceivably
force,
right? So it's just a fairly complicated problem that you don't want to dismiss too quickly by saying it all goes away unless it's precisely as we've seen. But it is the motivation for the multiverse, another motivation, because one explanation simply would be there are many, 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 many universes in which the parameters have all different values across those many universes. And in most of those universes, the conditions are not amenable to living systems like human beings. But in one of those, or a small number of those universes, the conditions are amenable. And of course, we're in one of those universes because we could not exist in any of the others because the conditions are not correct. The analogy is if you go into a clothing shop and you want to buy a sports coat, and you say, I want to buy a sports coat, and you see only one on the rack, and the person brings it over and it fits you perfectly. You're like, wow, that is so fortunate that it was just the right size to fit me. But if you go into an actual clothing shop, when there's hundreds of different sports jackets on the rack of all different sizes, when the person comes and brings you one that fits, you're not surprised. Of course, there's one among the many that works for you. And so if you have many jackets, it's obvious why one will fit. If you have many universes, it's also pretty obvious why one will fit the conditions necessary to our existence. And so it is a natural way of avoiding the problem that you're making reference to. The specialness of this universe goes away if it's one of a grand collection of possibilities.
Yeah. If I went into a shop and they had a sports jacket in just my size, I'd feel pretty special. I'd feel pretty chuffed about that. If I discovered that actually they'd gone into the back and picked from a billion different possible suit jacket sizes, I'd be a little disappointed by that. I'd be kind of upset. Do you feel a bit nihilistic at the prospect that it seems amazing, everything is perfectly tuned for us, but actually maybe not. Maybe we just happen to be in one of billions of universes.
I guess that's not where my self-worth comes from. I sort of don't look at the specialness of the universe or my place within that special universe. Rather, what fires me up is the fact that a collection of particles called a human brain, which is all that we are, collections of particles, can coalesce through an evolutionary dynamics to yield a structure that can think and feel and love and emote and create and illuminate and figure out quantum mechanics and figure out general relativity and come up with the idea of a multiverse and describe black holes and predict the magnetic moment of the electron. And that, to me, is the amazing thing, that matter, not infused with any divine force, not, in my view, structured by some divine plan, can, through the bare laws of physics, come together and do what it does.
It's It's definitely marvelous. I do think it sort of doesn't offer consolation in the way that feeling special does, because I feel like oftentimes people conflate the idea of something being amazing with something being like meaningful. People like to say things like, okay, I believe that there is just the universe, but when I look at a beautiful night sky, I'm filled with awe and wonder, and that might be true, but it doesn't fill you with that sense of belonging in the same way. If anything, like, one person looks at the universe and thinks it's so grand and so brilliant that, man, I slot right into this, and they find their sense of belonging. Whereas some people look at the universe, they look at the same thing and they say, gosh, this is also big, and I'm just in a tiny little random neighborhood. Like, oh, I have no place here. I'm just randomly here. Like, which of those do you identify with more when you look at the universe?
They're both true.
Right.
I mean, I fundamentally believe that there is no cosmic purpose. There is no cosmic meaning. I do believe, and I'm open, as we discussed, to other ideas ultimately replacing this perspective if it made sense and if there was evidence, but I fundamentally believe that we are the product of physical processes and that we are physical structures, and that these physical structures just come together for a brief moment of time and then we disperse. And for that brief moment of time, can I feel alone and nihilistic? Yes. Can I feel connected and thrilled? Yes. Can I hold both of those ideas in mind simultaneously? Yes. And I do. And so, yes, at times do I feel completely at sea in this gigantic cosmos, crawling around on this nondescript planet, going around this ordinary star in the outskirts of the Milky Way galaxy? Yes. Can that make you feel small and lacking some sense of purpose? For sure. But at the same time, when I think about the fact that we've developed these mathematical ideas that describe that reality, it gives me a feeling of connection to that reality. I feel closer to the universe when I have a deep description that at least approximates some of the processes that take place. General relativity makes me feel closer to the cosmos, as does quantum mechanics. And so, yes, alone, and yes, connected, all together in one human mind that somehow is able to grapple with these ideas.
This multiverse situation that we were talking about before, do we have good reason to think that it might be the case outside of A, its possibility, and B, the way that it kind of conveniently does away with the trouble of things like fine-tuning or the trillions of ways that string theory dimensions could be folded in on themselves? Because, like, you imagined walking into a jacket shop and finding one that was perfect, and I'm imagining walking into a jacket shop and it's just like a tiny little store, somewhere in New York on like the second floor, right? And it just has a few jackets and a few pairs of trousers, and I try on this jacket and it is like perfect. I mean, it's the exact shade of blue that I was looking for. I send it to my camera guy and he does the little hex code and he's like, man, this is like exactly the right color temperature. The sleeves are the perfect length, like uncannily perfect. Like everything is great. It's even got like a name tag from the previous owner that says Alex on it, just by pure and I think, man, this is absolutely unbelievable. I'm saying to my friend, this is unbelievable. I can't believe every single time I look at it, something new that just unfathomably coincidental. And the friend says, okay, this is amazing. What must have happened is that there are actually like an infinite number of jackets that are sort of sat in the back. And every time somebody comes into the shop, they sort of bring one out by chance and hope that it's a match. And I suppose we must also have sort of existed in New York for an infinite amount of time so that this guarantees that at least once this goes right. And of course, you're going to be the one that gets it right, because otherwise you wouldn't be having this amazing experience. Compared to just what I naively experience, which is like one room and a jacket which fits perfectly, I would basically ask that friend to give me more reason outside of the convenience of explaining this coincidence to believe in that infinite set of jackets, to think that it's actually true, right?
I mean, in the end of the day, that's really what we do. We try to explain the confluence of data that seems to lock together with such a gratifying and impressive cohesion, just like your perfect jacket, inscribed in just the right way. And
this is that jacket. By the way.
it's beautiful. I agree with your cameraman. And so what we try to do is to write down equations that will give us some insight into how it could be that there's a process that starts in the Big Bang and results in the things that we are now experiencing. Now, are there certain things that might be pure coincidence? Like, could it be pure coincidence that the gravitational constant and the electromagnetic force have just the right values to yield the qualities that allow us to exist? It could be coincidental. It could be really causative. It could have been, had the values been different, they would have caused something else. And that something else, if it had consciousness, might be in the same quandary, saying, why were the constants just the right value to allow me to exist? And yet they'd be different than the constants that we have. And so you have to be careful about seeing things and being impressed at their uniqueness when they might not be unique, and impressed at how they are designed when they may not be designed. They simply may be what they are, and you are the result of those features. They weren't set in order to get you to exist. They were set maybe by some random process, and you are the output of that random process. What we do as conscious beings, we tend to look at our environment and try to explain it in terms that somehow give us a narrative, a story. And we love stories that somehow have a purpose. But these stories may not have a purpose. It may just be random events with random numbers that yield, based on their structure, certain outputs. And we may be the output of those random qualities.
So at risk of belaboring the point, because we're speaking quite generally here, in particular the multiverse, like I say, outside of this convenient explanation of certain phenomena, but not in such a way that it's like, a predictable, testable hypothesis. Just this makes some sense of what we see. Do we have good evidence outside of that for the multiverse? When I spoke to David Deutsch, he was firmly convinced. I mean, he said he doesn't believe in the multiverse. He knows that the multiverse exists. From sort of a quantum perspective, he's a many worlds interpretation type guy, so a very particular kind of multiverse. But he just thought that we had this evidence. It wasn't just a way of explaining difficult quandaries. Do you believe in the same way that we have like evidence for the multiverse, or do you tend to just treat it as a potential hypothesis to do away with these problems?
Yeah, I absolutely do not think we have evidence for the multiverse, and I believe I understand David Deutsch's perspective. I actually never met him, but I have read his books. And of course, I'm deeply familiar with the many worlds approach to quantum mechanics. And it is a compelling mathematical framework that we humans invented to describe these strange processes in the microscopic realm. Is it the only description of the microscopic realm that we have? No. There are other ways of talking about the phenomenon of quantum mechanics where you don't mention the word multiverse. You don't mention many worlds. And as of today, we don't know of a way to experimentally distinguish between these different approaches. So I think it's far too early to say that the many worlds, the multiverse version of quantum mechanics is correct. And that's only one flavor of multiverse. There are many ways in which you come upon this idea of many universes. You come upon it cosmologically, from inflationary cosmology with multiple big bangs. You come upon it in string theory with many different possible shapes for the extra dimensions. You come upon it also within string theory with something called brane universes. So there are many flavors of multiverse that science has bumped into. Absolutely none of them are at a level of understanding where we can say, yes, there is evidence for the multiverse. No, there is mathematical motivation based upon our attempts to understand things in the external world, but it is mathematical motivation for thinking about the possibility of a multiverse. So yes, I keep it in my toolkit as an interesting possibility that you break out when you don't have any other way of describing what it is that you're seeing.
Yeah. Is that similar to how string theory works, though? Like, I mean, we were talking before about how string theory is mathematically elegant and makes sense of some phenomena that we see, like the graviton and this kind of stuff, but we don't have any experimental confirmation. The way that you've just described the multiverse is something you keep it in the back pocket, but I don't think we have good evidence to believe it's true.
Yeah.
Are these sort of similar?
I would say it depends which pocket the theory is in. So yes, multiverse, back pocket.
Yeah.
String theory is like right here.
Right.
And the reason for that is to put quantum mechanics and general relativity together. We know we've got to do that.
Yeah,
and string
somehow,
theory
right.
does that. You know, the idea that general relativity, as we discussed, emerges from string theory. It's a real powerful way of thinking about why this theory might be the way to put these two together. It may be that general relativity is intrinsically within string theory from the get-go. And there's another story just like that for quantum physics within string theory. So that's why it's here. But yes, I agree.
That's your jacket pocket, not the heart.
That's wrong. Yeah, it's the correct size. But yes, I did mean the jacket pocket. Until you have experimental evidence for mathematical ideas, they do need to be viewed as provisional.
Yeah.
But I think I would put string theory one step closer to connection with physics than the general idea of a multiverse.
25 years ago, The Elegant Universe is published, introducing a lot of people for the first time to string theory. How has your confidence in string theory fluctuated since then?
Yeah. So, look, 25 years ago, I would have thought that the conversation we're having right now would focus upon all the experiments that had been done that connected to some of the predictions of string theory.
Predictions about God.
That's right. You know, predictions about supersymmetric particles and things like that. That didn't happen. And yes, is that a disappointment? I'd have to say, honestly, it is a disappointment. But on the mathematical front, 25 years ago, if you asked me, will we understand the fundamental exact equations of string theory in any domain? I say no, we'll only still have approximate equations. We have exact equations in particular domains right now. Will we have a way of talking about space and time in a radically new language than Einstein's general theory of relativity? I said, well, it'd be nice, but I don't think. We have that language now that's emerging from these studies. And I could go on with the mathematical progress that exceeds anything that I would have imagined 25 years ago. So that has certainly increased my confidence in the capacity of these ideas to really give us a rich description of reality. But again, I would have hoped that we would have the observations that would at least tentatively connect with some of the ideas of string theory, and that we've not been able to do.
It's going to cancel out such that, roughly speaking, you're about as confident as you were? Because it sort of sounds like string theory is awesome and great, but like, yeah, it could be false. It's, as you say, it's sort of in the jacket pocket.
Yeah.
Is that where it was 25 years ago as well?
Well, again, I think part of it is the psychological question of a youthful physicist looking at the world as, you know, this spectacular landscape of discovery versus a somewhat, I like to think, more mature perspective on reality, which is a little bit more subdued. And so, yes, when you put those together, I would say the level of confidence is fairly close. But that's an amazing thing in its own right. The fact that these string theoretic ideas have been subjected to an additional quarter century of mathematical investigation by some of the greatest minds that this planet has ever produced. And I'm not putting myself in that category. I'm talking about string theorists as a community. And the theory have stood up to these mathematical assaults and has yielded riches that are completely unexpected and enormously gratifying. That is amazing. That is not something that's minor. That is a major step in the direction of developing an idea that may well be the correct description of reality.
And if we wake up tomorrow and discover that this is the correct description of reality, somebody has somehow experimentally confirmed string theory, what does that change? Does it change much outside of just our understanding? Hey, isn't that interesting? Does it change the way that I live my life? Does it change the clothes that I wear or what time I get out of bed in the morning or anything like that?
It's always difficult to answer a question like that in real time.
Yep.
But I think quantum mechanics gives us a beautiful case study where we can look at it over a longer stretch of time. Because if you were talking to Erwin Schrödinger, Niels Bohr right now, and it was 1920 something, 23, 24, and you say, look, if this quantum mechanics thing pans out and it really is experimentally confirmed, will that change my life? Will it change when I get up in the morning? I think they would have said, look, we're talking about atoms and particles. And if that isn't the kind of thing that determines how you live your life, then probably quantum mechanics will not have a big impact on you. And yet, here we are 100 years later. And because of quantum mechanics, we have been able to control matter, harness matter on microscopic scales, yielding the integrated circuit, yielding all manner of technological progress. The fact that you have the cell phone, the fact that you have a personal computer, the fact that you have any kind of technological device is because of the work of quantum mechanics. So has it affected how you get up in the morning? Yeah. Now when you say, hey, Siri, 8 o'clock wake up call, that is because of quantum mechanics, fundamentally speaking. And so could the same thing happen with string theory if it's correct? Will we be able to harness matter in new ways and do things that I can't even imagine today? Yeah, I can imagine that possibility.
Yeah, that's interesting. People often probably neglect to think about that when it comes to the utility of physics. I mean, there's a big debate about how many resources the government should put into space travel or science or whatever. And there is quite a myopic view that this is not worth this particular project. It's not worth this amount of time or money to work out if, you know, this book is made of strings or particles. Who cares? Forgetting that there are always unforeseen consequences of these physical theories.
Yeah, absolutely. You know, there's some calculations that suggest, and it's pretty obvious if you think about it, you know, a significant fraction of the gross national product of any major nation on this planet can be traced back to quantum physics. And so I don't like that as the main motivation for doing science, because it then suggests that we should just do applied physics, because it seems like that's the justification and the motivation. Whereas even with quantum mechanics, it was not applied physics when people were developing Schrödinger's equation or Heisenberg's uncertainty principle. It's the fundamental ideas which later generations can take over and then apply. So you don't start applying, you start fundamental. But yeah, can these ideas change how we live? Absolutely.
I wanted to ask you, in the time remaining, a question which mystifies me, which is what on earth the time remaining means. I listen to people talk about the discovery of particles and forces, and that somehow forces can express themselves at fundamental levels as particles. That to me seems kind of strange, that gravity can be a kind of particle, but okay, I believe you. Time, I just don't even know what it is. I don't know if it's a force, a particle, a substance. I don't know if it exists. When you think of time, when you're describing time to somebody, just crudely speaking, what image is in your head? Like, how are you conceiving of this thing called time?
So the first thing I should say is I also do not know what time is, and I don't think any of us do. Is it something that we humans impose on the external world just to organize our perceptions into some coherent narrative? Is time more than that? Is it fundamentally stitched into the fabric of reality? Are there realms of reality where there is no conception of time at all, and it just exists in a way that doesn't change in the manner that we usually think of when we're talking about dynamical changes through time? I don't know, and nobody does. But how then do I think about it? Pretty much the way you think about it. I think of time as something that allows for change. Time is the environment within which things can differ at one moment versus another. And in fact, the way we note that time has evolved is by comparing things, whether it's the second hand on a clock, the readout on your iPhone, or the color of my hair 25 years later compared to what it was when I was much younger. That's how we mark the passage of time, by virtue of change. But is time more than that? I don't know.
Well, most physical mathematical calculations work in both directions, right? Like if you take almost anything and just reverse it as if time was going backwards, it all works out the same.
Yeah.
So it's very difficult to discover why there is this arrow of time that takes us from past to future. And it feels like it does take us there. I can get up and walk forward or back, or I can stand still, but I can't do that with time, even though I'm told time is a dimension a bit like those other spaces which I can manipulate. I find it impossible to wrap my head around. But also when somebody says maybe time is just an illusion or something we impose into the world, that doesn't make sense to me either, because I think, well, to impose something is something that's done through time, and so I don't think I recognize that possibility, the idea that time is some kind of human construction. Is that what you were sort of suggesting?
It could well be, or it could be deeper, but the problems that you're referring to are real ones, and we have made progress on at least some of them. In terms of the arrow of time, why does it seem to have a direction when, as you rightly say, the laws of physics as currently constructed, they're agnostic between what we call forward in time and backward in time. They work in both directions equally well. And we believe it has to do with entropy, this idea of disorder. And we believe that entropy has this tendency to increase over time. And we furthermore anticipate, we can't prove, that the Big Bang was a state of incredibly low entropy, very high order. And we have been living through the degradation of that order for the last 13 billion years. So why, when you drop a glass and it shatters, doesn't it unshatter? We believe because the glass is carrying forward that drive toward greater disorder. It could unshatter, at least in principle. It's just so incredibly unlikely, because to go from disorder to order is a very difficult maneuver. To go from order to disorder, that's very simple. Just drop the glass and it shatters. And so that at least gives us some insight into why there is this direction to time. But if you step back and say, but what about time itself? Like, why is there this thing called time, and why is it different from space? Why can we so freely navigate through space, left and right, back? It doesn't matter. There's no constraint. Why is there this constraint on time? I can't really give you an answer to that question.
And you can conceive of space, but you can't conceive of time in the same way. It does make me wonder if there is a similar kind of like fine-tuning problem for time. Of course, time ticks differently if you're near a mass of gravity or if you're traveling close to the speed of light. But presumably there's some kind of like ratio by which, as the mass increases of a gravitational object, the time dilation increases.
Yeah, we have a formula for it.
Presumably that is something that you could also like tweak in principle, where as the mass increases, the time ticks proportionally even more slowly than it actually does right now. And so
1 minus 2 GM over C squared R. I mean, that's we actually have a formula
you took
for
the
it.
words out of my mouth. That's right. And so I suppose what I'm just wondering here is, when we talk about this like fine-tuning argument for God's existence, or like multiverse type stuff, is time one of those qualities? Because it seems to me like unnatural to think of it in that way, because I think of time almost as the space in which all of that's happening. But is there also this fine-tuning of the way that time works too?
I think that gets closer to a psychological question as opposed to a scientific one, in the sense of the fundamental nature of time. I think we beings have these structures, and these structures in our heads change on certain time scales, and those time scales evolved. And so were the massive Earth very different, or if we were on Miller's planet orbiting Gargantua in a black, would it be perhaps that we would evolve differently and our sense of time would be different? Sure.
Well, I mean to say that like the fact that if I say I like double, say I'm orbiting a black hole, and I then double the mass of the black hole, there will be some proportion by which the time dilation increases. I'm imagining a world in which the laws of physics are tweaked such that when I double it, time dilates in the opposite direction, let's say. Let's say that when you go towards a black hole, instead of time slowing down, it speeds up. Like, I don't know if there's anything in principle preventing the laws of physics from having been that way, but presumably that would cause all kinds of problems for the harmony of the universe, analogous to how if you turned up the strong nuclear force, everything would fall apart.
Sure. I think that's absolutely true. But the one thing I would emphasize is when it comes to special relativity time dilation, going near the speed of light and time slowing for you relative to somebody else, or general relativistic time dilation, you go near a black hole and time elapses slower for you than it does for somebody far away. You don't notice that.
Yeah.
Because it's time itself, according to these ideas, that is slowing, which means that all physical processes that take place in time slow down. So your watch slows, but your thoughts also slow. So from your perspective, nothing has changed. And so, yes, could it be that you would disrupt the structure of reality if you had the qualities that you're making reference to? Sure, I can certainly imagine that. But bear in mind, it's not the individual that their experience somehow changes. It's only by comparison to two widely separated individuals or widely differing in their motion individuals where these differences will emerge. The individual doesn't realize it at all.
Well, I do seem to realize an increase in the speed of time when I'm having an enjoyable conversation, and that is what has happened over the past hour or so that we've been talking. Brian Greene, thank you so much for taking the time.
My pleasure.
If you enjoyed that conversation, you might like my previous episode with David Deutsch for more talk on the multiverse. You can watch it by clicking the link that's on your screen. To support my work and get early, ad-free access to videos, subscribe to my Substack at alexoconnor.com. Thanks for watching, and I'll see you in the next one.